all of the work that we have done so far is about to pay out and pay out big. This is why. First, we're going to see that under the assumptions that we have put together, under this additional structure that we have introduced into the maximization problem, the solution of the problem is going to have some very nice properties. First, it's always going to exist. Always. And second, it's going to be unique. And third, it's going to have some very nice economic intuition. So let me spend the next few minutes showing you why. Let me start by reminding you what we have seen so far, which is that many of the economic problems that we will encounter in this course have additional structure that introduces nice properties in the maximization problem. And these properties are, first, that the objective function can be divided into a benefit term and a cost term in an additively separable way, such that the total payoff from taking action X is the benefit minus the cost. Second, we have seen that in many natural circumstances, the level of the action that can be taken has to be non-negative, i.e., X has to be greater or equal than 0. And last but not least, we have seen, and we will continue to see, that in many examples, the benefit and the cost function satisfy the following properties. Benefits increase with X, in other words, the marginal benefit is positive, but the derivative of the marginal benefit, or the second derivative of the benefit, is less or equal than 0. The cost function increases with X, so the marginal cost is positive. The derivative of the marginal cost, i.e. the second derivative, is non-negative. And furthermore, it is not the case that both are equal to 0. These conditions or properties on the benefit and cost functions of the maximization problem are so important and so useful that we're going to pick a name for them so we don't have to write this mouthful every time we encounter them. And we're going to call them the concavity conditions. We're going to see that the solution in this case takes one of two forms. And which form it takes depends on the following condition, which is whether the marginal benefit at 0 is less than the marginal cost at 0, or whether the marginal benefit at 0 is greater or equal than the marginal cost at 0. Let's look at each of these cases. Consider this one first. This particular case looks like follows. We have that the marginal benefit at 0 is less than the marginal cost. And then we know by the concavity conditions that the marginal benefit function is either going to be flat or decrease. So let's say it looks something like this. And that the marginal cost function is either going to be flat or increase. So it looks something like this. So what does the optimal look in this case? I claim that it has to be the case that X star, the best that you can do, is equal to 0. Now, why is that the case? Well, suppose that you are at X equals 0 and you consider taking the first unit of the action. What is that going to do to your total payoff? The marginal cost of taking this action is all of this height, this. The marginal benefit that it gives you is only this. So therefore, if you remember your calculus, taking that first unit of the action entails a loss in your payoff of approximately this area. And things only get worse with subsequent units of X that you may take, because the distance between the two curves, the marginal cost curve and the marginal benefit curve, is only getting larger. So the additional loss for any additional unit of X that you take gets worse and worse. Now consider the other case in which the marginal benefit at 0 exceeds the marginal cost at 0. That case looks as follows. We have, for example, something like this. As before, the marginal benefit function is going to be either flat or decreasing, say something like this. The marginal cost function is either going to be flat or increasing, say something like this. In this particular case, I claim that the solution is given by X star given by the equation, by the solution to the equation, marginal benefit equals to marginal cost. Let's see why. Well, clearly at zero, being at zero cannot be an optimal or a maximum, because if we take the first unit, we get an increase in our payoff equals to this height, and only an increase in the cost equal to the marginal cost at zero of that unit equal to this much. So that will increase our total payoff by all of this much. We can keep playing this trick until the point in which the marginal benefit curve and the marginal cost are equal. At that point, the total increase in payoff obtained by taking the extra unit cancel each other, and we don't get anything. Any subsequent increases after that will entail a loss of total payoff because the marginal cost curve is above the marginal benefit curve. Here is another way to think about the intuition from the solutions that we just characterized. Consider what is the marginal value of taking an additional unit of x, let's say, of delta x, which we can denote by the marginal value of the objective function, which given the additive property is going to be equal to the marginal benefit minus the marginal cost. Now, we know from the concavity conditions that the marginal benefit function is either going to be flat or decreasing, that the marginal cost function is either going to be flat or increasing, and that implies that the marginal value of taking an additional unit of x on the total payoff, which is the sum of these two, is going to have to be decreasing by the concavity conditions. Okay? So the basic idea here is that the value of taking an additional unit of x is never increasing, and in fact is getting worse and worse. Now, what does this mean? This then means that there is a very easy way of thinking about the solution, which is you start at zero. If the marginal value of taking a unit of x is positive, let's say if the marginal t looks like this, you take it. And you keep going until the marginal value of that thing gets zero, and then you stop, because any subsequent unit is going to entail a loss in payoff. Next, I want to make several remarks about the material that we have seen so far in this subunit. The most important part is all of the structure that we have imposed so far is not enough to guarantee that a global maximum exists. And the reason why is a little bit of a technicality, but I think it will provide further intuition about the material. So it's worth going into it in detail. Consider the following example. This is going to be 1, a horizontal line at 1. This is x. And suppose that we have a marginal cost function that looks like this. For example, is 1 minus e to the minus x, and a marginal benefit function that looks like this. B prima, for example, 1 plus e to the minus x. Now, notice that these functions satisfy the concavity conditions. B prima is greater than 0. It's easy to check that B double prima is less than 0. C prima is greater than 0, and C double prima is greater than 0. So given that the concavity conditions are satisfied, the objective function is concave, strictly concave, we're maximizing the positive range, and all of the assumptions 1 to 3 are basically satisfied. And yet, it's easy to see that a global maximum doesn't exist. Let's see why. It doesn't matter what x you pick, what level of x you pick. At that level of x, the marginal benefit exceeds the marginal cost by this much, which implies that it's payoff improving to move to x plus dx, to move a little bit to the right. It doesn't matter what x you pick. That is always true, because basically the marginal benefit function and the marginal cost function are asymptotically convergent to 1. So it's easy to see that we can have these extreme technical or pathological conditions, if you want, that satisfy all of what we've seen so far, but in which a global maximum does not exist. The second comment or remark that I want to make is that something called the crossing conditions are going to rule out this problem. Now, what are the crossing conditions? We say that the problem satisfies the crossing conditions if the following is true. And remember, we are looking at a problem with this economic benefit minus cost structure. So it has to be that either the marginal benefit goes to 0 as x goes to infinity, or the marginal cost goes to infinity as x goes to infinity, or both. Now, let's see what this means in a graph and why it's helpful. If I plot x, if the first thing is true, it's telling me that the marginal benefit is going to 0. So it's approaching asymptotically 0 as x gets very large. The second means that the marginal cost is getting very, very large as x increases. Clearly, if either of these is true, or at least one of them, we cannot have the example that we saw a moment before, and that is going to imply that the marginal benefit and marginal cost curves cross at some x. And as we're going to see in a second, that is going to guarantee the existence of a unique optimum. The third remark is that the assumptions that we have imposed so far, including the concavity condition, the crossing conditions, are enough to guarantee the existence of a unique global maximum. And let's see why this is the case. The assumptions say that we are going to be in one of two cases. Either we are in the case in which the marginal benefit is always below the marginal cost, in which I won't repeat it for the reasons we've seen before, the unique global optimum is x equal to 0, or we're going to be in a case in which the marginal benefit at 0 exceeds the marginal cost at 0, but because of the crossing conditions, the marginal benefit and the marginal cost curves cross. And I claim that that point at which they cross x star is the unique global optimum. Let's see why that is the case. Well, clearly, you would never want to stop producing at a point less than x, because at such a point, marginal benefit exceeds marginal cost by this much, and producing an extra bit more will increase your payoff. Similarly, you will never want to produce an amount greater than x star, because at that point, the marginal cost exceeds the marginal benefit by this much, and you could increase your payoff by decreasing the level of x by a tiny bit. This is the only point at which marginal benefit is equal to marginal cost, and you cannot play that game of increasing the payoff by either decreasing or increasing the level of x. And that is the unique global maximum. Now, the result that we have developed in this section is so important that I want to highlight it for you as a key result of this first unit. And it basically says, if you have a maximization problem that has the economic structure that we have assumed that satisfies both the concavity and the crossing conditions, then there exists a unique global maximum that has one of the following two forms. If the marginal benefit at 0 is less than the marginal cost at 0, then the solution is 0. Otherwise, the solution is to be obtained when marginal benefit equals marginal cost. I am aware that for many of you, the material of the last 20 minutes has not been trivial and perhaps has been too mathematical and too abstract. But please believe me that if you understand the key result that I just gave you, it's going to give you a lot of power to solve problems throughout the course and to understand the key intuitions and the key reasons for some very, very basic and important results in economic theory. So I urge you to go back and look at these results if you have not fully understood it, to really grasp. It's really an investment not only in the class but in your understanding of economics. The good news is that now we can put this into use, and you're going to see how quickly we can solve very interesting problems just by applying what we have learned so far. So let's do some examples.